Today we'll be going over page 6 through 8 of the homework. Now, page 6 is a review of all of the naming we've been working on so far. With naming, a lot of times on the test, students tend to get what type of compound it is confused. Basically, compounds for our purposes are going to be broken into either being ionic, which means they contain a metal, versus covalent, which means they have no metals. If you look at the periodic table, with the exception of hydrogen in the first group on the periodic table, everything else, groups 1 through 13, would be considered a metal. The exception being boron as well, which is a metalloid. However, if you have only nonmetals in a compound, which would be carbon from group 14, nitrogen and phosphorus from group 15, oxygen through selenium in group 16, and all of group 17, you will have a covalent compound formed if you have 2 or more of these. I X'd out the noble gases because generally in level chemistry we will not have any reactions with the noble gases. Their octet is considered full. So when we look at naming, if it is covalent, this is the naming that uses prefixes. And when writing a formula, there's no crisscross. For metals, if it contains a metal, and let's say just any other nonmetal, all you have to do is list the metal and change the nonmetal ending to IDE. And this would be group 1, 2, aluminum, gallium, indium, zinc, cadmium, and silver. If it's an ionic compound with a transition metal, which would include groups 3 through 12, and also things like tin and lead, and anything under the staircase that wasn't mentioned over here, you will use Roman numerals. And for both ionic types, if you're writing a formula, you crisscross the oxidation numbers. So that's just kind of a checklist for your brain before you start. For example, if you're looking at number 1, this is definitely an ionic compound. The easiest way to tell is only transition metals have Roman numerals. So this would be a formula that we would be required to crisscross on. SN is a formula for tin, and this is 10(2), so I'll put +2. Sulfite, using our chart, would be SO3 -2. When these charges are exactly the same, they cancel each other out. So your final formula is just SnSO3. If you feel more comfortable putting it in parentheses, you may, but it's not necessary. So the next one is obviously the same thing. We have to crisscross because we see a Roman numeral. And this would cancel out very similarly because iron is 3 and phosphate is 3. So it would just be FePO4 because the 3's would cancel. If you see prefixes, if you see a prefix, it is a covalent compound. It does not you never, ever, ever crisscross on covalent compounds. If there's no metals, you write it just like you see it. Trisulfur would mean there are 3 sulfurs. Monoxide would mean that there is 1 oxygen. Again, it's not necessary to write ones, but if it makes you feel more comfortable about covering your bases, we don't mind if we see them. Aluminum will form ionic compounds, so thus we need to crisscross this formula. Al is +3, phosphorus is -3. My goodness, we gave you a lot of examples of cancel out. Okay. On the bottom part, it's asking you to do the reverse. It's giving you the formula, and it's asking you to come up with the name. For number 9, calcium is definitely a metal because it's in group 2. So we are going to name the metal. And if you're left over with 2 or more capital letters, it's kind of an indicator to go look for this on your polyatomic ion chart. So we go down to carbonate, and it's CO3 -2. So we just name it calcium carbonate. We never change the ending of polyatomic ions. Phosphorus is most definitely going to be a nonmetal. So phosphorus and oxygen are both nonmetals. So this is a covalent compound. So we use prefixes. This would be penta for 5. So we have 5 phosphorus. So pentaphosphorus. And 6 is hex, and then oxygen, since it's the second word, would change to IDE. So it'd be pentaphosphorus hexoxide. So basically for the bottom part, the first thing you have to identify is that first element a metal or a nonmetal? If it's a nonmetal, you simply write the prefixes. Disulfur, heptaoxide. However, if there's a metal present found, you cannot use prefixes. So this would just be aluminum bromide. On page 7, we're asking you to identify what shape the molecule would be and whether or not the molecule would be polar or nonpolar. We've given you the dot structures for some of the elements. In number 1, we gave you the dot structure for both elements. Your teacher simply wants you to connect the dots to make a pair. So you can see the outer ones on this oxygen have a friend, they're paired. However, these need a pair, and these need a pair. Each time we draw a line, that's called a bond. So the yellow lines are called bonds. Okay. In this case, we made a double bond. For our purposes, the only shape we have that can make a double bond is called linear. Also, if you only have 2 elements, it must be linear. Now, to tell about polarity, you need to think about it being symmetrical. Is it the same on both sides? So I would visually split the molecule, okay, right down the middle there. Does it mirror it? Is it the same on both sides? If both of the elements are the same, it will be nonpolar. So oxygen is a nonpolar molecule. I'm going to skip around a little bit so y'all can see examples of things that are not linear. So I'm going to go to number 4. Number 4, they only drew the central atom. So they want you to plug in these 4 hydrogens. Hydrogen only has 1 valence electron. It only has 1 valence electron total. So we would connect the hydrogens around the carbon. And we would need 4 of them, so we put 1 on each of carbon's lone dots. This shape kind of looks like a cross or an intersection. This is called a tetrahedral. Okay. And we do that same concept of splitting the molecule. In this case, I'm just going to cover up the center atom. I'll put a nice car there. Is everything on the outside of the center atom exactly the same? Well, sure, they're all hydrogens. So that means that this would be non-polar. If even one of these was a different element, like say this one was chlorine, it would make it a polar tetrahedral. But in this case, since everything surrounding the center atom is the same, we would call it nonpolar. Go ahead and do a few more examples just so y'all have some different ones to look at for your homework. Here you have arsenic, and it says you have 3 fluorines. So I'm going to add 3 fluorines. Again, you can only add elements, and fluorine has 7 valence, by the way. You can only add a bond when an electron is not paired. So that kind of helps you see where you plug in the Legos. Okay. This is called a pyramidal. It has 3 bonds, so we call it a trigonal pyramidal. Now this is different than a planar because as you see there's a lone pair on the center atom. This lonely pair up here makes this a polar molecule. Because again, if you covered up the center atom, there's certainly fluorine on 3 sides, but the 4th side is not the same. Anytime you have a lone pair on the center atom, that's going to immediately tell you it's a polar molecule. For the next one, we need to add 2 chlorines to this sulfur. So again, to me, it's like plugging in Legos. You can kind of see that you need something to bond onto this one and something to bond onto that one. Chlorine has 7 valence electrons because it's in group 17. Okay. Now this only has 2 bonds, so it's definitely not trigonal. Trigonal basically means 3 bonds. Okay. You can see that these lone pair are going to bend the molecule. So this is actually called bent. It's the same shape that water is. And because if you cover up that central atom, it has lone pairs on the center atom, it's definitely polar. Bent molecules and trigonal pyramids are always polar. I'm going to take us to the back, and we're going to do one more example that we haven't done yet. Boron only has 3 valence, so it should be very easy to see where these 3 fluorine are going to pop in. Now, you might be thinking, oh, this is just like this one that we just did on the other page. But the only difference is, see how this arsenic has the 2 lone pair above it? Boron does not have that. This is called a trigonal planar. And I like to call it planar because it is plainer than the one we just did. This one, you can imagine a cheerleader pyramid, and the cheerleader's up here with her pom-poms. But if it's a plain trigonal, a planar, it won't have the pom-poms. Now when you cover up that central atom, since there's no lone pair on the center, and all of the atoms on the exterior are the same, we would say that this is nonpolar. If one of these fluorines were changed to chlorine or iodine or whatever other element, it would make it polar. But since all of these are the same atom attached, we say it's nonpolar. So I'm going to go ahead and review the patterns with you. Boron molecules are always going to be trigonal planar. Carbon and silicon have 4 valence electrons, so they tend to be tetrahedrals. Nitrogen, phosphorus, and arsenic all have 5 in their outermost shell, so they tend to make those trigonal pyramids, which are always polar. And oxygen, sulfur, and selenium are often bent. And if you have diatomic molecules like fluorine, chlorine, bromine, those are going to be linear.